there are no conflicts of interest for the speakers and no financial relationships that are germane to the content of these presentations. Let me just talk a little bit about Dean, and I'll talk a little bit more about Martine as well, but hopefully she'll arrive. But some of you know the incredible work of Dean Kamen, who is in the Manchester, New Hampshire area. Attended the Worcester Polytechnic Institute, but dropped out before graduating, not because he couldn't handle it, but because because he was kind of on his own path ever since he was a young child on infusion pumps and auto syringe, and inventing, which eventually became kind of his major thing that he continues to work on now in ways that you could hardly imagine. And obviously many people know what a Segway is, and Dean was the inventor of the Segway. I think he has something like 490 patents or something like that. Kind of amazing. The thing I like most about Dean isn't any of those things. It's his excitement and his engagement and his willing to try to make the world a better place. And it's not about profit motive. It's about really making lives better for people. I've been privileged to work with Dean more recently in projects that are pretty exciting for doing dialysis at home, hopefully, using tools for monitoring, even things that we've developed here that he'll talk about. But just a remarkable individual that never ends with excitement. And every time we talk, he says, I got 3 things, and then I'll hear your 3 things. And we each barely get our 3 things done, but we always end up in the same place trying to move forward. So Dean, welcome to Dartmouth-Hitchcock. I'll introduce Martine, and then we'll just say hi to her because she won't mind not having a major introduction. She's done so many things like Dean. She's an American lawyer and entrepreneur. She graduated from UCLA with a combined law and MBA degree in 1981, then worked in Washington, D.C., first in the field of communications, satellite law, and eventually in life science projects like the Human Genome Project, just a small project like that, and is founder and chairman of United Therapeutics. She also created GeoStar and Sirius Radio, to name a few things. But you know, this day where we celebrate the gifts of Debbie and Wayne Granquist for these grand rounds, we're privileged to really celebrate this because of what Wayne and Debbie have done. Our first Wayne and Debbie Granquist speaker was Nancy Ann DePaul, who worked in the White House on healthcare reform. Our second speaker was Toby Cosgrove, CEO at the Cleveland Clinic, and this year we've brought Martine and Dean together to really talk about the integration of science and medicine with technology. And I can't think of 2 better people. And we'll start out with Dean. And Dean, welcome and thanks for joining us.
This is a very, very shortened version of my normal, shameless groveling and begging for support for my not-for-profit FIRST, for inspiration, recognition of science and technology. I normally wouldn't do this now, but I heard that Martine's going to be a few minutes late. She doesn't need to see this. She's seen it a few years ago and got hooked, and in fact, not only is a major supporter of FIRST, but she's joined the board, and she's a huge supporter. But I said, if we're going to get started, rather than leave her out, because you need to hear from her. She is just remarkable. I said, why don't we take 2 minutes to listen to the voice of God, Morgan Freeman, explain what FIRST is. He visited our championship a few years ago and was so excited to see what these kids are doing. He turns to me and says, Dean, how can I help? I said, Morgan, you could read the phone book and people would be transfixed. So why don't you put together a video that we can send to potential corporate sponsors, universities and schools to help us keep growing. By the way, we've grown a little. We started with 23 teams 25 years ago, all in New Hampshire. I had moved up here and decided we were going to create this entity. Hutch, running your engineering school, was there in his striped uniform as one of our referees. But over the years, with 55% compound annual growth, we went from 23 teams in year one. We're in our 26th year now. We have 46,000 schools in 86 countries, 3,700 corporate sponsors, virtually all of the Fortune 500, 140,000 volunteer mentors working with the schools. So he came and did what's turned into a 2-minute and 12-second video that tells you what FIRST is. Last year, or a few months ago, after the championship, so many international teams were pushing us for how do we officially make this, not just an invitation to these 86 countries that showed up at our championship, 100,000 people in St. Louis. They said, form an international group. I went to the guy that prepared that famous 1-minute ad by which Steve Jobs announced he was back at Apple, and it was played at the Super Bowl to convince the world they're back. And I said, give me a 1-minute piece. That's not what FIRST is. That's what Morgan does, but why it is. And I sat with him for 2 hours. He said, Dean, in 1 minute, you're going to... I said, yeah, you got to keep just telling people it's not about robots. Robots are just an excuse. They're just a tool. It's about kids and confidence and a global network of people that can work together instead of generation after generation with the self-inflicted wounds of culture fighting with each other, arbitrary political boundaries separating everybody. He says, and I said, by the way, John, this famous producer, I can get you Morgan Freeman, I can get anybody you want. He goes, don't need Morgan for this one. I need a 7-year-old girl. So I'll first show you 2 minutes of what, and then, let me get to the end, I'll show you 1 minute of why there's a FIRST.
This is the Super Bowl. The Super Bowl of smarts, that is. It's a life-changing competition. It's kids having fun, competing, working together to dream up, design, and build robots.
It's just an exhilarating feeling. It's like I'm using power tools.
They're having the hardest fun they'll ever have. And they're becoming our next generation of engineers and innovators. First, come out! For inspiration and recognition of science and technology. My teachers were some of the greatest influences on my life by challenging and trusting me. These mentors got me to understand that I could do anything I put my mind to. FIRST mentors are changing kids' lives every day. Professional engineers, teachers, parents, teaming up with young people not just to build robots, but to build confidence and self-respect.
I'm around people that I can get along with, that we can talk computer lingo with.
FIRST was founded by one of our greatest inventors, Dean Kamen. Dean saw that kids mostly look up to sports heroes and movie stars.
So we said, if we've got a culture now that's obsessed with sports and entertainment, let's inspire these kids to be big thinkers the same way Shaquille O'Neal can inspire them to spend dozens of hours a week bouncing a ball.
Our president agrees.
Scientists and engineers ought to stand side by side with athletes and entertainers as role models. And here at the White House, we're going to lead by example. We're going to show young people how cool science can be.
250,000 kids aged 6 to 18 compete at all different levels. In 2 FIRST Lego Leagues, the FIRST Tech Challenge. Then at the high school level, the FIRST Robotics Competition.
The only difference between this sport and all the others is every kid on our teams can turn pro. There's a job out there for every one of these kids.
Students who take part in FIRST are 50% more likely to go to college and twice as likely to major in science or engineering.
I definitely know that I want to pursue engineering.
Once they've tasted what the power of knowledge is, that it can be fun and rewarding, they won't go back.
There's no doubt FIRST works.
10 or 15 or 20 years from today, some kid in those stands will have cured Alzheimer's or AIDS or cancer, or built an engine that doesn't pollute. Look at these kids. They're the future.
I feel like I can go and do anything I want to do because of this program.
Someone took the time to guide and inspire me. It changed my life. Take some time. Go to usfirst.org.
And by the way, we have 182 universities that sponsor teams, and last year at the championship in April, we handed out $34 million in scholarships. But among the longest-term supporters among all the universities from year one were two. The one that I spent the best 5 years of my life as a freshman at, and Dartmouth. So thank you for that. But as I said, I go to John and say, I need now something that convinces people this is way more than robots, and it needs to be a global network. And he said, Dean, I've listened to what you said. Let me give it a shot, but I don't need Morgan. Here's a 7-year-old girl.
This isn't a robot. It very well may have hydraulic arms, a drivetrain, and a circuit board, but this isn't a robot. This is a lesson in humility, hard work, and collaboration. This is a CrossFit workout for the muscle upstairs. This is an apple for the next generation of Newtons. It's a lot of things, but this isn't a robot. This is a roadmap that leads straight to engineering. This is a rock to shatter 1,000 glass ceilings, a rope to pull a generation up and out of poverty, a sledgehammer to break down cultural barriers, and a universal language spoken in every nation on Earth. And because of that, this is a compass that can help point the way to peace. But please, don't think this is just a robot. This is Glastonbury for technology. This is mission control for the next moonshot. This is the Rosetta Stone to help translate the future. This is the sport that will help us win tomorrow. This is the software to program ourselves to cure cancer, build a clean engine, or step foot on Mars. But this isn't a robot. It's a machine to build the people who will change the world.
We are announcing the absolute real, not invitational tournament version where we had 86 countries last year, but on July 17th this coming summer from Constitution Hall in Washington, in cooperation of the National Academy of Engineers, the Royal Society, and the Chinese Academy of Engineers, we are unveiling international first, global first, and as I said, we already have 86 countries. And I see that one of the founding directors of International First, Dr. Martine Rothblatt, just showed up, so I will shut up.
So this is Martine and Dean, and I don't know exactly what you brought with you. Anything special?
My
something.
warm affection for Dartmouth Hitchcock.
Okay. Good. I think some of the interesting things that Dean and Martine are doing, I think, will be very interesting to you all, and we'd appreciate anybody's questions. We only have a limited amount of time, about 45 minutes, unfortunately, for these kind of geniuses to work with and talk to. But maybe you want to start, Dean, since people already heard you, and then bring Martine into the discussion about where things are going and what you're working on?
So I've spent about, I don't want to talk about how many decades in the medical field, and almost every project we work on, people think they're very different. This is an electromechanical pumping system. This is a stair-climbing autonomous robot, an iBot that can go up and down stairs with a human payload. And I say to people, all my projects are pretty much the same. I'm here to get people, I hate to say it, Doc, out of a hospital. I've never met anybody that likes spending time there. They never find it a really cost-effective place to have a vacation. So when my older brother was still a med student, he's an MD, PhD candidate at the time, pediatric hematology. You got to have a special gift to do that. We started making pumps for him. He realized, or people around him at Yale, at Harvard at the time, realized that these were little battery-operated things. You could put them in the pockets of adults instead of in the neonatal ICU with his patients. And in the pocket of an adult, patients could go home instead of being stuck to an IV drip. Then they realized you could give continuous things like insulin with bolus capability to get better long-term control. So we started a whole company around building drug delivery, but it was primarily to get patients, again, out of hospitals. Then we started building other equipment to get them home. Then we started building dialysis equipment, not to improve the stuff in a hospital, but to make it so simple and easy to use that the first home peritoneal dialysis machines we made, the goal was make it the size back then of a VCR. Nobody knows what that is anymore, but it's and we said the entire control system has to be a big green button that says go and a big red octagon that says stop. And it has to have a cassette that you can put in it wearing hockey gloves and foggy glasses, because most of these patients have various kinds of serious limitations. But we said if somebody could put this cartridge in and it self-purges and self-primes, it comes pre-sterilized, they plug themselves in the morning, they unplug themselves, the machine says ready at night and finished in the morning. We were told we were nuts. People are never going to be allowed to do essentially life support outside a hospital. This is the late 1980s. When everybody tells me we're nuts, I'm always thinking, that's a good project. If it works, it'll make a difference. We shipped our 500 million therapy cassette for that thing last year. It became standard of care for peritoneal dialysis, but we realized 4 or 5 years ago that's 8% of that market. We decided we've got to make the same kind of capability that is safe to be used by an individual patient at home alone if it's hemodialysis, which, as you can all imagine, has potentially more serious issues. So we had to add all sorts of full-time onboard monitoring and safety systems. But then we realized what it really needs, besides the best technology, the best human interface, it needs connectivity, and it needs to have docs at the other end of this that are taking care of and monitoring these patients. That's why God invented Jim Weinstein, Imagine Care, and all the things he's been promoting for decades. And we realized that maybe we can do a whole set of new trials. We can get this new machine through the FDA. By the way, we did 1,081 full therapies on 22 patients over a 6-month period. Every therapy went to completion. Every patient loved it. Within 9 days of finishing that first clinical, it got a CE mark and it's legal in Europe. The FDA came back to us and said, it would be interesting to do another study, maybe non-inferiority. And I said, that would be interesting. And if you happen to have 18 months and $50 million, I'd be happy to try that. But we think there's got to be better ways to move forward more quickly. And I'm hoping with frankly, the prestige, the credibility, and the expertise of wanting to do remote and outpatient therapy that Jim Weinstein brings, we're going back, and we hope to revisit that issue along with Dartmouth-Hitchcock and accelerate the ability for that thing to come forward. We met Martine Rothblatt, who is a synaptic storm. You'll hear about her life. And we realized with her background, obviously, literally as the founder of Sirius Radio, and there's things that are more serious than radio that need to connect people around the world, like reliable and protected monitoring. And we started working with her because of some drugs that she would like patients to get, again, outside of a hospital environment, and she'll tell you about some of them. And we have some great technologies to make literally patch-sized things to make that possible. But soon after meeting Martine, we realized how deep her interest is in all things medical, particularly related to orphan situations, and particularly related to advancements in technology like regenerative medicine. And then in the category that we now frequently refer to as this only happens to Dean, I not only meet Martine and she starts telling us about the fact that she's decellularizing and recellularizing tissue, which is 21st century medicine, but she's doing it with equipment that looked like she raided a a Home Depot, and we said we could probably build you some integrated systems to make bioreactors, to make this automated and reliable and safe and consistent, and then we can get it to scale and start supplying some of the 300,000 people waiting for kidneys and lungs and livers. So we started working on that. The next thing we know, the Department of Defense announces this huge RFP for somebody to figure out how to bring regenerative medicine out of the laboratories of all these brilliant people around the world, or certainly around the country, that are eventually going to win Nobel Prizes. But we got to get it out of their roll of bottles and get it up to scale. And I went back to Martine and said, let's do this. And I went back to Jim and said, you got to help us do this. And so we now have a parallel path moving towards which we're going to be building regenerative medicine equipment and the resources to give to all of these advanced researchers so that they'll have the tools to move more quickly, and will build out a process of bringing it to manufacturing scale, bring it through the FDA, and really meeting the needs of people that are in desperate need of new organs. I will now shut up.
What do you think, Martine? Is he crazy or what?
Actually, I think he's a blessing. I don't think that there's anything crazy about Dean. I first learned about Dean's work when, as he mentioned, we needed a medicine to be delivered to patients outside the hospital, and previously they were only receiving this medicine inside the hospital. And we were able to take the insulin delivery device that Dean referred to and tweak the electronics on it just a little bit so it could be used for the medicine that we provide to patients with pulmonary arterial hypertension. It's a different kind of condition, different medicine. And I very quickly realized that Dean is singularly capable of, I think, anybody in the whole world in moving fluids from one place to another, especially fluids that are human scale. I don't know what he's done in dams and the Erie Canal level things, but when it comes to human scale fluids, whether it's water purification, blood purification, what have you, Dean is truly a genius in that area. And everything that we do in healthcare, the body is one big hydraulic system, and the heart is an absolutely amazing hydraulic machine. So to me, when we get into the realm of using technology to help biology, I think Dean is just an outright blessing to the world, to the country, and certainly to our state of New Hampshire. So it's been my real honor and pleasure to work with Dean. One of the projects that we're working on right now is to try to do something to close the huge yawning gap between the number of patients who die from end-stage organ disease and the number of patients who receive organ transplants. And that gap is on the order of 5 orders of magnitude. I mean, it's hundreds of thousands just in the United States alone, the difference between the people who die of end-stage organ disease, especially heart and then secondarily lung disease, and the number of patients who can be listed for an organ transplant. This is despite the fact that half of all Americans have agreed to become organ donors. And when asked in a hospital, the number of people who agree to become an organ donor becomes up to 75%. So even if 100% of people became organ donors, it wouldn't solve the problem that we have of this huge gap of organ transplantation. So what we are trying to do, working together in partnership with Dean, is to get into a realm of organ manufacturing, that we are now in the time and point in history when it is practical to consider an organ to be something that can be manufactured in a bioreactor and then shipped in real time to patients to have transplanted. And we are undertaking this organ transplant manufacturing process in several different ways. Department of Defense is extremely interested in this because when, for example, a soldier is injured in a battlefield situation and has serious trauma to their organs, obviously if they have to go on a wait list for a half year, there's going to be no hope for them. So one way we do this is there are a large number, in fact, the large majority of organs which are donated for transplant are not actually able to be used for transplant because they've been ischemic for more than an hour, and transplant surgeons are rightfully cautious about using such organs in transplantation. We, together with our partners, have developed what we call ex vivo perfusion technology. So perfusion, you hear again the movement of fluids in and out, to, in essence, revitalize organs that have been ischemic for even an hour. And hundreds of such patients have now been transplanted with dead, quote unquote, lungs, hearts, and now kidneys. And the results that have been published show that the survival of the recipients, even a year later, is no different than the survival of people who are transplanted from adjacent operating rooms in the same hospital. So it's a wonderful testament to the plasticity of human organs. It gives us a big cause about the logistical barriers that we face in getting organs from all sorts of donation scenarios into a perfusion chamber. But if we can get them to the perfusion chamber, we can perfuse them and, in essence, manufacture that organ by restoring it to save thousands of lives. Our next method that Dean referred to is we take pig lungs and decellularize them in a type of bioreactor that Dean's team in Manchester, New Hampshire has developed. And so in a detergent type of bath, which is strong enough to remove all cells and microbial matter, but not so strong as to destroy the delicate collagen scaffold of the lung, we're able to remove all of the antigenic matter from the pig and then recellularize that with adult cells of the type that are necessary for the lung, epithelial, endothelial, and so on, different cell populations. And these then recellularized organs, I believe, will be able to start being used for transplantation within just a couple of years. We're now doing it in both. We've accomplished it several times in small mammals, and now we're doing it in large mammals. So there's a ready supply of hundreds of billions of mature adult cells from organizations such as the American Type Cell Culture, ATCC, Lonza, other companies like that, which again ultimately receive these cells from anatomical donations of people who have died. They then use different types of enzymatic and other technologies to separate out the different cell populations, and they sell them to companies such as ourselves. So when we recellularize a pig's lung that has previously been decellularized with human adult cells, it's actually another type of lung donation that's just occurred kind of through a couple of processes that allow us to stretch out time and turn this into a continuous manufacturing case where we don't depend on somebody dying in kind of real time the same day in order to get the lung to somebody else. The third method that we're using to manufacture organs is to genetically modify the porcine genome, the pig genome. And here we are teamed with the company Synthetic Genomics, formed by Craig Venter, one of the leaders of the human genome decoding team, to make a number of modifications in the pig genome. So when organs grow inside a new pig, they are human friendly. They're not 100% exactly human, but in terms of its immunological, coagulatory, hematological properties, it will surpass what's called hyperacute, acute, and even chronic rejection in a human recipient. Here now you see it's even more of a manufacturing process because it can occur by the tens of thousands. We've already achieved a number of, in fact, all of the records for longest lived organs in primate models of humans have been achieved with these genetically modified organs we've done. At the NIH, our lungs routinely last more than a year in baboon models. And I'd say are probably just about a couple years away from the first human transplant. And when we started this, the longest you could get a pig heart to stay in a baboon was just a matter of days, and now it's routinely over a year. Our lungs now are routinely over a week. When we started, it was minutes, less than an hour. The lungs are a very delicate organ. Kidneys are routinely a half year now. So this is, we are very close to kind of like the breakthrough to light speed here and being able to use genetically modified pigs as bioreactors for an unlimited supply of organs. Last but not least, the most exciting project that I have with Dean, and I think what will end up being the focal point of the DoD funding, is to actually print a 3D scaffold, which is the framework for organs, lungs, kidneys, livers, hearts, out of bioabsorbable material, and even including cells themselves, and then to cellularize these non-animal sourced scaffolds with cells that are derived from stem cells of the intended recipient. So they are inducible pluripotent stem cells that have been differentiated back into the species of cells needed for that particular organ. And in this way, the patient is literally receiving their own organ, and there is no question about coming up with fancy methods of what we call immunological tolerance or chimerism to get the patient to accept the organ. It would be a no-brainer. I mean, it will be tolerable. It's your organ. Of course, these sorts of things can't be done on demand in a day, but the vast majority of patients with end-stage organ disease, you've got a few months of time to be able to go ahead and print and grow them a customized organ, whereas these porcine organs would be ready for an on-demand situation like the DoD requires. So all of this requires a lot of movement and very clever, intelligent movement of fluids back and forth in very highly precise ways, different types of fluids, different types of viscosities. And for all of this, Dean is a genius. And I feel very, very honored and fortunate to have our company working so closely with Dean's company and now in partnership with Dartmouth Hitchcock as well.
Thank you, Martine. These are amazing people, right? It's so interesting to listen to your work in FIRST, Dean, and growing the future generation of young minds in the science and technology, why Martine is growing cells to create whatever she wants. So somehow we need to bring these together. But I think it's a really exciting. I don't know if the group has questions, but I really wanted this to be a conversation with Dean and Martine.
I'm Neil Boucher. I'm one of the physicists on site here. You already touched on 3D printing. Could you touch on how the advances in material sciences has impacted your work and what you've been able to use in your research?
So it's, this, again, it's an amazing consequence of the collaboration of Dean and I that we reach out, our networks combined seem to produce 100 times more people than either one of us could do independently. So I had been and continue to work down the pathway of different types of collagen and collagen blends, and to use techniques of 3D printing that provide a long time for each layer of printed material to cure. Because ordinarily with collagens today, you could not use the rapid 3D printing techniques to make a scaffold because the heat would be too quick and you'd end up melting these layers. But working with a company called 3D Systems, which is a leader in this area, we figured out a way to very slowly print the scaffold, which really doesn't matter because if you're printing, it just means how many printers you have running in parallel. So if you have, say, if it takes a year to print a scaffold, just to take an extreme number, and it wouldn't actually take that long, and if you then say you have like 1,000 of these 3D printers running, then you can come up with something like 3 scaffolds a day, which right there, for the lungs alone, that would represent a 50% increase in the number of lung transplants that could be done today. So not to mention that they would be autologous lung transplants if cellularized with your own cells. So that's one approach. But then, you know, Dean comes to me, and it usually starts with a phone call, and he meets this brilliant bioengineer.
He's like not a bio guy.
Oh,
He's a pure mechanical engineer who spent 15 years in tribology. To those in the medical field, tribology, he studies.
I'm a physicist here, so tribology is...
So lubrication, oil, interactions on surfaces. He was a world's expert. He was a consultant for NASA on all the things that have to work in space, that have to be lubricated, but with no vapor pressure of an oil that's going to disappear. His expertise is entirely mechanical engineering. What does he have to do with any of this?
So it turns out this individual, unfortunately, is diagnosed with cancer. And he's a young man and a young professor, and he has a aggressive form of cancer. And I'm not saying anything out of school because he's very public about it. He gives commencement addresses at universities about it. And he basically says, I've got to cure myself. And he begins working on a way to print in a gel substrate that is able to be made more and more dense as a substrate is extruded into it. So this particular type of material that he uses allows you to print an organ into the substrate. It's called Carbopol. It's actually a commercially available material. And as you print it, the density tweaks up ever so slightly in this material, so that one of the big problems with printing a delicate scaffold is how is it going to withstand its structural integrity. And so with his technology, we're actually printing in something which is sort of like on the boundary between a liquid and a solid. And then at the end, he's embedded this Carbopol liquid solid material with a certain type of molecular bond that melts away under an appropriate frequency of light. So at the end of the day, you're able to just kind of melt the structure and then take what would then be a complete functioning organ and move it into a person. So this is, I want to emphasize that we are at the level of millimeters of material here, but that is the proof of concept. And everything that Dean and I have done, it starts like at the millimeter level. And I think, you know, one of the things that might differentiate Dean and I from the average Joe is a lot of people would either just throw up their hands as, well, this has never been done, or a millimeter, what's the big deal about a millimeter? And I'm just using it as a generic term for like a proof of concept. But I think what Dean and I tend to see is like, well, if it could be done in 1 millimeter this year, then in another 6 months with such and such activity, we can then get to 10 millimeters. And while 10 millimeters is not a functioning heart in any way, but from 10 millimeters we can get a larger, and we see a logical Gantt-like critical path chart that gets you from step to step. And of course there are setbacks, and of course there are failures along the way, but we're persistent. We're very persistent individuals, and we see stumbling blocks as opportunities to learn something and do things a little bit better. And if you will be persistent over a period of like, 10 years, it's almost anything can be accomplished. We started off not even able to get satellites into low Earth orbit, and 10 years later, we were able to land people on the moon and have everybody watch a live telecast of that. I know that's a prosaic example, but there are tons of examples like that in every walk of life, including in healthcare. And one of the things I'm very proud of here today is to officially sign up our company, United Therapeutics, and its 1,000 employees with the ImagineCare network of Dartmouth-Hitchcock, because I believe even though that may be kind of like at a millimeter level, it's bigger than that, and it's a fantastic control center. I believe that that's a prototype of what all of America is going to be like, where your health is monitored pretty much non-invasively, algorithmically, proactively, and you begin to see survival tick up, mortality tick down, and finally people attribute it to what will be the truthful cause, which will be proactively, algorithmically nipping problems in the bud via the Imagine Care Network.
Thank you, Martine. It's kind of amazing. Oh, do you want to ask a question? Go ahead, Barbara.
I have a question. I'm a neurologist here, and I'm in epilepsy. So my question is actually to like basically, when do you see a brain transplant coming along? But more specifically, which sounds kind of prerogative, but more specifically, do you see any chance that a scaffolding could be built and neurons be cultured on it that could replace some missing or damaged tissue in the brain?
So the latter question, I think that 100%, I feel 100% confident about that. And there's a huge need for that. So all you need, again, is just like Dean and I always quote back to each other, Margaret Mead's adage, that it only takes a small group of committed, I'll say scientists, in this case, Margaret Mead, I think, said citizens, but let's just say scientists, to change the world. And in fact, that's the only thing that ever does. So I think if there was a team of people committed to that, the technology toolkit to do exactly what you said with regard to growing neurons and scaffold, and then being able to transplant full nerves to a patient, and in fact doing that as well with differentiated cells from the patient's own progenitor stem cells. I think all of that is with hand and could in fact be done within a handful of years and maybe commercially within 2 handfuls of years. A brain transplant, that's beyond my ability to see. These first kids of Deans who are growing up, learning, cognitive engineering, the way we learn reading, writing, arithmetic, theirs is like cognitive engineering. Those will be the kids that will be able to see the way to do that.
I would add, if you asked me that a few months ago, I'd say I have no idea about what organ. Go talk to Martine. But it's amazing how much attention you get when you go around the country saying, the Department of Defense is ready to give us a few $100 million if we can put a stake in the ground and make this real. And so I now have a small group of people that have been talking to every major research center around the country that's doing anything in regenerative medicine. And we've been trying to prioritize, and it's complicated because, frankly, making a complete lung, which has so many different kinds of cells and so many different scales physically that they have to operate over to get that oxygen transfer, you need surface area like a football field, and make a kidney and make a liver. But then
tennis court.
Yeah.
It's not as bad
as
as a football
field. I tend to exaggerate. So, and then the more we looked at it, yeah, but can we just make a 2-dimensional thing like skin? Well, can we roll it up and make a tube to make a fistula that can be used to make a shunt? Well, maybe a 3-dimensional. Well, maybe a piece of an organ. Well, maybe a piece of cardiac tissue. So we have been laying out a very detailed plan now, and we have found all sorts of people that are come out of the laboratory, started little companies, and I can assure you, much to my surprise, the people that are closest to actually having something that we think is ready for prime time to bring to scale are the people that are saying, well, I can't make a whole organ, but I can make a neuron, I can make a connection, I can help you jump that open circuit because somebody had severed a spine. I would argue to you, and you'll see some of them now, in the next few weeks as we put our final proposal together, high on the list of what we're going to explain is that while it may not be the biggest need in terms of, the press sees somebody with a new artificial heart or a new lung, the ability to make skin, the ability to make bone, and the ability to do various things with neurons is going to be, in the short term, the ones that are most likely to be doable. And by the way, in terms of a brain transplant, I would tell you there'd be no market for it because most people don't even use the one they have. But anyway, that's a separate subject. But again, the ability to do that is really getting close. And if I could ask Dr. Weinstein to lend us a little bit of faculty time here so we can help look at making sure that the ones that are working on things that are doable will actually start to meet the needs of a significant population, because our process of trying to respond to this RFP is a complicated intersection of how doable is it, how many people can it serve, and how core is it to be a stepping stone to further work. And neurons are very high on a lot of those lists.
There's a process where you take, I won't say simple tissues, but easier to imagine, whether it's on the skin or a shunt, and start to do some clinical work with that in trials in an actual clinical environment that we hope to help Dean with across the country. And then as you get to things like kidneys, which it's interesting, the timing, Martine, you talk about years, not decades.
Right. It certainly is years, not decades.
Yeah.
And that's not just my opinion. I think that would be a consensus of the people in the field right now.
Yeah, I mean, the point is this is moving so much faster than we imagine. And so as we think about our future, we're having our Board of Trustees here today helping us think about the future. It's really complicated to kind of live today in the world we live in, which is fairly complicated, and imagine this world tomorrow. And can you speak a little bit to that from your viewpoint, your seats, because you run companies, you interface with lots of universities and lots of funding agencies. What's your perspective on healthcare, even though you're not in it, per se, day to day?
This may sound like an ad for our sponsor. It is not. I think, besides this whole thing that we've been talking about for a few minutes of regenerative medicine being a really big thing on the horizon, I think something that's even closer and will have an even bigger impact for a whole lot more people than just the ones that need a kidney or need a liver. Americans right now are facing an ugly reality. They can't afford to get the health care. They complain about it, but unless you're lucky enough to be around a big university medical center, you're not even getting close to state-of-the-art care anywhere in this country. And there's a perfect storm coming that's either going to tear us all apart or bring us all together. And I think that perfect storm is connectivity and real-time ability to move information and knowledge and even video systems for doing a diagnosis. How often does the doctor actually have to touch it? By the way, we'll give you a haptic response. We'll let you have better digital ways to even do that. But connectivity and sensor technology are intersecting with some of these other advances in medicine in a way that, while it would be so much more expensive, it's almost impossible to justify. And certainly every little community can't build out their We've seen what happened when this country tried to scale up massive technologies that are all underutilized. They don't have enough professional people behind them to even make use of the data. And the example, and this is not an ad, but when I came back to Jim Weinstein and said, the only way that we're going to make home hemodialysis a reality, and by the way, just this should burn into your brains, 1.4% of all patients that receive any money from Medicare, Medicaid, from CMS, 1.4% consume 18% of all federal reimbursement. That 1.4% are end-stage renal failure patients, because frankly, cancer is a very considerate disease. It either kills you, which is very efficient, or these days you can cure a lot of it, which is also very efficient. That's true of heart disease. Way more people have heart disease than end-stage renal failure, but they either recover or they don't. The fact is, a chronic condition like end-stage renal failure is $100 billion a year of reimbursement if you include the comorbidities. $100 billion a year and growing. What's worse than that, it puts people in these torture chambers a couple of days a week. It gives them a sub-appropriate therapy, keeping them barely alive. Nobody is happy with the outcome. It's unbelievably expensive. What do you do about that? You find a way to move them home, to give them better care, better quality of life, and lower cost. How do you do that? It's a life support system. I told you what happened when the FDA. So when we said, how are we going to create a system that would make this doable, we've got to bring in the other two things besides our magic little machine. We have to bring in the world of connectivity, which is now becoming accepted on many levels, though there are issues. And we have to bring the medical community to believe that in centralized places, at the other end of that connection, we can put enough clinical support that this makes sense, that the risk and the reward are going to be reasonable. But that's going to take a change in mindset of the medical community. Hospitals are going to become a place for an acute condition. You got run over by a bus or you need a heart transplant. For just about anything else, you'd rather be at home. The reimbursers would rather have you be at home. Your family would rather. The iatrogenic stuff goes away. And forward-thinking docs could probably figure out how to make all that work by integrating these advanced technologies and these capability to connect people. The trouble is you find very few people in high-level positions in hospitals that are doing anything except worrying about bringing people in to the 19th century model. And when we found out that Jim Weinstein, for more than 20 years, has been leading this organization to go around to places in South Dakota and North Dakota that don't have access, and 20 years ago, when connectivity was not a word in the dictionary, he was worried about getting better health care out to more people in more remote places, we said, why don't we work together and take your Imagine Care, and besides giving people, you know, a remote way to measure their blood pressure or a CO2 monitor, what if we gave them really sophisticated stuff and we could pile on to get the efficiency up and the leverage up of Imagine Care? What if we could put out in these homes really good monitoring systems and really good control systems that could literally in real time take care of patients with end-stage renal failure, with critical, for instance, brittle diabetes? What if we could use Imagine Care as a platform to really build what the world's going to need, efficient, distributed medical care that goes to the patient instead of this very unsupportable, ineffective way to bring them to places like this. So I think over the next few years, what's going to change healthcare most is the millennials will not tolerate the nonsense and the pace at which we're moving away from it. The proof of that is, I'm not going to get into politics, but we have two candidates from the two big parties, neither one of which has got a lot of passion behind it by most people. But you look at the most recent data, the millennials as a group are more in favor of the third party candidate than either of these two. They're also more in favor of getting their health care this way from somebody they trust at the other end. The proof is they've made a big deal. They've made multi-billion-dollar companies out of Fitbit. Well, frankly, connectivity should be way more than talking scales and stupid nonsense that tell you how many steps you took. But those kids, but those kids are now willing to use these technologies for their health care, for their serious health care, for their family that might need dialysis or cardiac monitoring. And I think Dr. Weinstein has been ahead of that curve for 20 years, and I hope in the next few months we're going to, working with Imagine Care, build a couple of platforms, together go to places like the VA, the FDA, and CMS, and show them that we can move this stuff way faster than it's been moving in the past.
CMS has been real. This is the largest expense, single expense for CMS is dialysis, and I think the idea of being able to bring this home with home monitoring has tremendous potential. Martine, do you have a thought about timing? You know, you said it's not decades, but when do you think we'll see the first artificial kidney transplant with a 3D printer?
Yep. So, you know, I often am kind of pinch myself because I feel we're all in the middle of an amazing forest here, but we don't really see it because we're in the middle of it. As just a couple of examples of that, a couple of like, you know, I'd say skin pinchers, if you will. Within the life of virtually everybody in this room, the overwhelming conventional wisdom worldwide, all the scientific elites, was that decoding the human genome was not possible. It was too big, too complicated, and way outstripped the computing power that was available. And yet, not only was it done, it was accomplished ahead of schedule. After that miracle, while that miracle was done, and after that miracle was accomplished, The conventional wisdom of everybody, the black and white in every biology textbook, was that the dogma of biology tells us that cell differentiation only goes one way. It goes from an undifferentiated cell to ever more differentiated. And if you tried to say, well, maybe it could go the other way, you'd fail your class in medicine and biology, cell biology, molecular biology, whatever you were taking. And yet, within just really the past 15 years, and to a large extent the past 10 years, that has been proven not to be the case. And we now know with iPS cell technologies and various versions of that, that cells can be redifferentiated, differentiated cells can be brought back to an undifferentiated state, and then redifferentiated into dozens and dozens of different cell types. And this is, by the way, both the gene sequencing and the cell differentiation is not something that's so complicated to do that it's only being done now at the NIH or someplace with a supercomputer. Every university with any kind of a decent biotechnology capability, biology department or a bioinformatics department is doing it themselves with equipment that they can buy from numerous vendors. So this is two revolutions in medicine, one within 15 years, the other one within 25 years. So when I don't think that, you know, it's crazy at all to say when you see all of these revolution going on, and that all you are going to do is use 3D printing, which is yet another revolution in technology that went from science fiction to teenage kids 3D printing, you know, shoes and stuff in their living room, to take this technology and to go ahead and print a scaffold and cellularize it either with cells that you can buy as a commodity from multiple vendors by the billions, or that you could cellularize it with an individual's own cells using a tried and true iPS technique. I think this is much less a stretch than sequencing the human genome, or reversing the dogma of biology, or in my case, launching a transmitter into space that provides 200 channels of radio in every little nook and cranny throughout North America. This is a much smaller step to do the 3D printer. And I will tell you that some of the top experts in the kidney field are confident to me. They have put it in signed contracts that we're funding, that before the end of this decade, the first end-stage renal disease patient would receive a genetically modified xenograft that would be made tolerable and transplanted together with a tolerance inducement protocol that could give that individual an expectation to live a good 20 years or so with that renal xenograft. That's before the end of this decade, like 2019. And I would say easily within 5 years from that point, you would have a completely animal-free solution with a 3D printed scaffold and either allogenic adult cells or iPS-derived cells from the individual themselves, providing the cellularization and functionality.
We have time for one or two questions. Yes, please.
I'm another physicist in radiation oncology, and the WPI trained engineer in me thinks this is all amazing. However, you know, this is quality grand rounds, and the other side of me here has a question for you. As you're implementing these new regenerative tissues and things, are you also implementing a system to monitor outcomes and assess like quality of life, and how you're going to feed that back to determine whether or not this is really a useful engineering advancement and implementation?
So, in my first conversation with the guys at DOD, who were determined to do this quickly and want 5 years, I said to them, guys, if all the engineering were done today and all the medicine and clinical and physiology were done today, this is so radically different. The regulatory process and the reimbursement process, if it doesn't change dramatically, is going to push it out. And I said to them, in the proposal we make to you, I believe we should include, for instance, the FDA right up front, instead of the model that the FDA now has with just historically, you make your thing, you deliver it to them, they tell you whether they like it or not, and they send you away. They're a regulatory body. I said, but there are other regulatory bodies that we have in our society that work differently. When you want to go build a new building, like a hospital or a school, you don't show up at a town, go to the building department, the regulators, and say, I'd like to build a building. And they don't say to you, well, knock yourself out. Go build a building, spend all your money, and when you're all done, we'll come look at it. And if we inspect it and we like it, you can move in. Otherwise, we'll tell you to tear it down. No, they say, here's what you need for a permit. Tell us what you're going to do. We sign off on that permit. And then when we come, if you build what you said you built, there's no issue. I said, let's try a whole new concept, not just to build organs from scratch. Let's build a process to move quickly on the regulatory side to keep pace with these miracles. I think they're open-minded to that. I then said to them, again, this is not another ad for our sponsor. I said, please, we've got to go and get a bunch of clinical people that are connected around the country to show that if we can scale these things, because you've asked me to go into these labs where these geniuses that are going to win a Nobel Prize one day have a roller bottle with some magic in there. But you don't need a roller bottle full of this. You need a plant that's making 300,000 of these things this year. Well, we got to make sure that the community of clinical people understands them, understands how to deploy them, can monitor them, can help us go forward. So why don't we find some clinical institutions that have been dealing with those issues for a long time and include them in our proposal? And that's when I went groveling back to Jim Weinstein and said, I think our proposal has to have a little special edge to it. And you're in 38 states, and you've got 70 million patients that you have access to. Why don't we show that we know how to bring things to scale, leveraging that? I believe personally that Martine Rothblatt is, if anything, being conservative here. The rate at which we've been improving these printers, and you've got to come, we just finished the clean room version of a new one. We are now making printers that have resolution and repeatability with various kinds of materials that don't put any shear force on it. They don't act like a bubble jet. They don't need to be sintered with a laser. We're using, to somebody else's question, some incredible material science technology and some incredible media, like these liquid-like solids, but we're now able to make structures that you couldn't make any other way. And I believe that's conservative. I think making sure that the entire community, the regulators, the reimbursers, the clinical community, and the public are kept up to speed on what's going on here so that we can make reasonable choices about how much risk and how much upside we're willing to deal with.
Martine gets the last word.
Well, with regard to quality, as you were asking your question, I was thinking back to the newscast that occurred with the first patients at the Mayo Clinic in Jacksonville who had received our restored lungs. And one of the patients was a woman, and she took the news crew into her garage, which was filled with oxygen tanks. And she'd been dependent on oxygen for 2 years. For various reasons, I think that she would maybe have never made it to the top of the lung transplant list and would have ended up dying. And the expressions of love and gratitude that she showed, that she was able to see her grandchildren growing up with this lung that, I can't emphasize this enough, it was on its way to the trash can, as are 80% of these donated lungs from the brain-dead donors, not even talking about the donors from cardiac death. 80% of the brain-dead donor lungs are in the trash can. And she got one of those out of the trash cans. Because of our fluid pumping technology, we were able to get it into her. Her joy, her happiness, that to me spoke an Encyclopedia Britannica worth of quality of care.
Thank you so much. Thanks for joining us today.